So we should make sure the parentheses around the F part are a pair, the parentheses around the G part are a pair, and then we also have those parentheses that were already in there for us around the whole integrand.
I forgot the X.
Yeah, and then at this very end, we have to make sure to fill in that dx. And we get 11.33. And in general, I'm going to say round to 2 decimal places unless otherwise specified. So setting up the integral for these is the important part. Once we get the integral set up correctly, you can calculate it on, and should probably calculate it on a graphing calculator or Desmos. There will be some of these that are would require more integration techniques than we're going to do in this class. So don't get stuck trying to do it by hand. If you want to challenge yourself, that's fine, but definitely do it in technology. So this is the way we can think about where this area between curves comes from. We're doing this sort of exterior area minus the interior area, which really comes down to just doing that integral of f minus g. So I am going to go to our actual sort of formal definition of where this area comes, of the definition of the area between curves, which is also in the book on page 382. So if we look at the conclusion of this, then a equals the integral from a to b of f of x minus g of x dx. So this is where we got to at the end of the previous example. So that's what we can use every time here. Our interval of integration a to b, and then our two functions that we are finding the integrals between.
If it's a negative, if it's on the negative side, would it be from the furthest left to the right? So it'd be like -5 and -1 for A and B.
A, B is always small, then big. So yeah, if it was -5, 1, A would be -5, and or -1 would be up here. So we will always be doing the smaller. Let me start over. AB is an interval, and we always write intervals small, big, no matter what. For our integral, in our class, we will always be writing the small number down here and the big number down here. There are a bunch of funky things we can do with integrals and change that kind of thing, which has a sort of domino effect of how it changes other things. But for this class, we're just doing straight, smaller number on the bottom, larger number on the top. But there is something we have to pay close attention to in this definition, and that is this part. f of x is greater than or equal to g of x. Most of the time, the two functions that we're trying to find the area in between are going to be called f and g. That does not necessarily mean that they're always in this order. F is always the function on top, or excuse me, the first thing in the integral is always the thing that is greater, which literally just means it's higher up on the graph. And g is always the thing that's less. So if we have a graph, this could be f, this could be g, and in this case we would be doing f minus g because f is on top. So we're going to see a couple of examples where we might need to put the g in front. So this is just a general f and general g, but really the thing that needs to go first is the function that is on top in the graph. So that will come up in a little bit. So let's just start with an example. So our question is find the area bounded by f of x equals x squared plus 1 and y equals -1 for x greater than or equal to -1 and less than or equal to 3. So this is another phrasing that means the exact same thing. The area bounded by these things means the area with all of these things as its borders. So we will always want to look at a graph first because it matters which function is higher on the graph. And so you could just plug those two things into Desmos or a graphing calculator quickly. This one is not too hard to make a little sketch of by hand. So we have this f, which is x squared plus 1. So that's just a parabola with 1 as its y-intercept. And we have y equals -1, which is just a horizontal line at -1. So the graph does not have to be perfect. The important thing is that we see what the area is and what the relationship between these two graphs are. So then we also have these bounds between -1 and 3. Again, this is not a perfect graph, but at least we can see that x squared plus 1 is on top and the y equals -1 is on bottom. And we're looking for this whole area that's bounded by these things. So that's our A. So it's okay to just quickly graph those on Desmos or a graphing calculator. Some of them might not be so nice to just draw a quick sketch of. But the key here is that f is on top, which means that that will go first in our integral. So our area is always the integral on the interval we're looking at. So x is -1 to 3. So those are automatically our limits of integration. And I'm just going to write f and g to start off with, just to highlight, or not f, y. Okay, I'm not going to do that because it's a little confusing with that y. A lot of times when it's just a flat line, a horizontal line, we use y instead of a g of x, but it's no different. We're looking at two functions here still. So our f is the x squared plus 1. And then the other function, the other boundary, is -1. So our f is the higher function, the function that's on top on the graph. And our g is the bottom, or excuse me, our y is the bottom function, the y equals -1. So that's the important part. This is the setup that we need. And we can graph this. I'm just going to sort of switch between Desmos and the graphing calculator. So just as a review of how we did this on Desmos, you can either go down to this little keypad on the bottom left, go over to functions, and then go to miscellaneous, and the integral is down there on the left. Click that. Or if we don't want to hit all of those buttons, we can just write int. So int, as soon as I hit t, it turns it to an integral sign. So we're integrating from -1 up to 3. And our function, so our f was x squared plus 1. And our y was -1. And so it will not do anything until we put the dx in there. So in this case, I didn't put parentheses around the f just because it really isn't necessary on that first part since there's no minus sign in front. But then we do minus parentheses the second function. And we get 17.33. So I just want to bring up Desmos one more time to note, like, it would be fine to simplify this inside first before plugging it in here. So the -1 would be a +1. So combining like terms, this would actually end up being a +2, and it doesn't affect our integral. So it kind of depends if you feel like you're more prone to mistakes, like when you're simplifying by hand, or if you're more prone to mistakes when you're entering stuff into the calculator. We can do either one. It's just really easy to make little mistakes with like minuses and parentheses in both of these scenarios. So just be super careful. So before we go on, I just want to sort of look at what's happening here. So our integrals, definite integrals, look at area on a graph. So when we first started talking about definite integrals, I mentioned this little dx represents the infinitely small width of all of these little infinitely thin rectangles. So we started off looking at the Riemann sums, which are rectangles to give us the area. But really when we do an integral, it's like adding up a bunch of little tiny line segments. So by doing our top function minus our bottom function, we are actually getting the distance between the top function and the bottom function. So it gives the length of each of those little tiny line segments that are then being added all together from -1 to 3. So we still have the same sense of area where we are sort of multiplying our width, which is the -1 to 3 part, with the height. But the height is changing along this whole interval. But the height at any point is given by that top curve minus the bottom curve. So it's still the same sort of sense of what area means for like a rectangular shape, but we're adding this possibility of having curvy parts.
So is area bounded basically the same as in between?
Yes.
Okay.
The bounded part is like if you put a fence on these two curves and then a fence at -1 and 3, we would get this sort of fenced in area, and that's what we're looking for. So let's look at one more and remember this. So I am going to put up a poll in just a little bit with a multiple choice of how to set up this integral. Did I? Oh yeah, okay, good. With 4 choices. And so we're gonna first look at the graph of this, and then I'm gonna give you some time to try to set up the integral on your own, and then I will put up the poll. So let's go ahead and just graph each of these on Desmos real quick so we can see each of them. So we have, I'm just gonna get that away. We have f of x equals -1/2 x minus 3. And we have g of x equals x squared minus 1. And we're looking at between -1 and 2. So here are our graphs. G is this parabola, which looks as we would expect. It's -1, so it crosses the y-axis at -1, and then we have this line below it. So I'm going to draw a little sketch of those on our paper. So we had, our G is a parabola that looks like this. And F is a line that looks something like this. So it doesn't need to be perfect. We just need to have the general spacing of things. So take a moment on your own to try to write the integral that we would use to find the area between these two curves, bounded by these two curves, between -1 and 2. That would be this space here. And in a little bit, I'll put up a multiple choice to choose from. And I'm actually going to move this so I can fit everything on the page. So we have 4 integrals here, a, b, c, d. All of them are going from -1 to 2 on the integration. They all have a dx on the end. The difference is what's happening on the inside. So based on these 2 curves and the graph that we see, the question is, which integral is correct? So I'm going to give it about 30 more seconds.
Hey, Madeline, I accidentally clicked skip poll. I'm on my phone, so I don't really know how to use it too much.
Okay. Yeah, I don't know how if there's any way for it to come back. So thank you for letting me know. I'll just make a note of that.
Okay, thank you.
Actually, if you are able to chat to me what your answer is, you could do that, but I don't know.
Okay, yeah.
All the phone capabilities. Okay. So if you haven't answered, you can just take any guess at this point, and I am going to close the poll very shortly. Okay, I am ending the poll. All right, so 69% of people chose option B. Which is correct. So our little formula for, I'm going to go back for a second. Our formula for area between curves was F minus G. But we have to remember the actual names of these 2 functions are not what's important. It's the fact that the greater function, the function that is higher up on the graph, is what goes first in those parentheses. So B is actually the correct choice here because the function g, x squared minus 1, is on top. So we have to do that top function minus the bottom one, which was f in this case, for this area to work.
And it will calculate both ways. I did try to see.
It does, and I actually wanted to just show that on Desmos.
Yeah.
Because we do get an answer each way, but so if we do integral from -1 to 2, is that what we were doing? Yeah. And so we are doing g, which is x squared minus 1. Oops. Minus f, which was -1/2 x minus 3. dx, so our result is 9.75. I'm I'm just going to write that down here. So that is our answer. So just to see what happens if we do put a into the integral and switch the order of f and g.
B should be negative 8.25.
What should be?
B, because that isn't that negative 9.75. That's the
Positive 9.75. B. So B was our g, which is x squared minus 1, minus negative 1/2 x minus 3. And we got 9.75.
how come mine gave me a negative 8.25? Oh,
I don't know.
maybe. I'm not. I'll play with it for a second.
Yeah, it sounds like it might be a parentheses problem.
Because I changed it to a positive, I put the negative through
Mhm.
and changed it to a positive and a positive 3. Or actually, I didn't change the positive 3. I wonder if that'll do the same thing. I'm gonna try it.
If you distribute that negative through, it should work, as long as it's all correct.
Oh yeah, I forgot to change the 3, and that made the difference.
Okay.
Ah, okay. I'd rather learn now than not.
It takes practice. So this integral here is a, so we did our g, the parabola, minus f, the line, and got 9.75. If we reverse the order there and do what option A was and do f first, the line, and then g, we just get the negative version of the same number. If you get a negative number on any of these area problems, something went wrong. All of them should be positives because we're actually looking for the area in the normal sense. So if we switch them, now we're doing the lower one minus the upper one. And if we start with something small and subtract something, it's going to continue getting smaller. So that's why we do not want to start with the bottom function. We always start with the top one so that we can end up with positive distance between those two functions.
So if we get a negative distance, then that would make it wrong.
Yes, so if you end
Okay.
up with a negative number, go back and check your work. So this is exactly why I say draw a graph first, even if it's not a perfect graph. We do need to know which function is on top and which one's on bottom. We have one more like this, at least one.
Corey, what you eating?
Hear me?
Yeah, you were unmuted for a second.
Okay, so the unmute is, yeah, classic Zoom life. All right, so next example, we want to find, oops, sorry. Find the area bounded by these two things.
So this one doesn't give us less than or greater than.
Yes. So this is only slightly different. So we're going to start the same way though, just by looking at a graph, because once we see the graph, I think that'll help us see what we're looking at here. So we have the area, or area bounded by f of x equals 6 minus x squared, and g of x equals x. I forgot what it was. X. It's x. So this is a more specific situation where we don't need those intervals given to us. Because on this parabola, 6 minus x squared, that's one of our functions, and then g of x equals x is our other function. And we can see that there is already an area bounded in here without giving x, an interval on x. So if we ever encounter a problem like this that doesn't give the interval that we are integrating over, we should be able to see the bounded area on the graph. So what we have here is this parabola and this line. Well, I missed the origin there. And so we're looking at the area in between them. So we need to find the limits of integration. Which just means when we do our little integration squiggle, what number are we starting at and what number are we ending at, which will be these two intersections.
So -3 and 2.
That sounds right. Let's look at the graph. So -3, yes, is the first x value. And then -2, exactly. And it's just well, it's not a coincidence. It's because x does this, but we're looking at the x values specifically. So we don't actually care about the y's in this case. We are looking at the x that we're starting our integration over and the x that we're ending. So we have -3 and 2. And you have two options on how to find those. One is graph. For these problems, it's totally fine if you just look on the graph and find those intersection points for limits of integration. If you like a little bit of light algebra in your calculus problems, we can do this algebraically. So if we're just trying to find where these two graphs intersect each other, we would just take f and set it equal to g. And then solve this equation. And we would get the same things. So you can't just do it by graphing, but if you want to do it algebraically, that's also fine.
Is there a way in Desmos to shade the area between the curves?
There's not. At least it's not like set up. I feel like there's probably a way to do it, but I don't know off the top of my head. Although you might be able to, if you just like Google does most shading between curves, I would be not surprised if something came up. But it doesn't just automatically do it, unfortunately. All right, so we now know the number we're starting at and we're ending at, our limits of integration, -3 to 2. So what comes first in the parentheses here?
Parabola.
Right, exactly. That parabola is up higher, so we would have the 6 minus x squared first. And then the x comes afterward. The parentheses are a little bit excessive in this case, and I'm just putting them in there for consistency. We have our first function minus our second function. But since the second function is just x, we don't actually have to worry about that minus sign distributing. So we could just write it as 6 minus x squared minus x.
Can you actually take the x off of the x squared? Or add it, technically?
No, because those aren't like terms.
Oh, okay.
Yeah, so this is as far as we could go. And I'll just switch back to the TI for a minute. So if we go to math and number 9, it brings up our integration setup. So -3 to 2. And we have 6 minus x squared minus x. And we get 20.83. I have a lot of repeating 3's in these examples. That's yeah. Anyway, okay, so 20.83. And these problems, just as a note in case you were wondering, since we are just talking about area on the plane, the Cartesian coordinate plane, we don't have any units here because there are no units on the xy axes. If we start putting these into integrals into application problems, we will have units, but for these we don't. Okay, we're going to do one more example of one added thing that can happen here. So we've seen that we need to check to make sure we're looking at the right function on top, and that's always the one that goes first in our integration. And then we've seen these ones where we're not given the limits and we just have to find them either by graphing or solving algebraically. So we have one more situation that we can come upon. So I'll give you a moment to look at these before we graph them. All right, so bringing up Desmos again. Our f in this case is 5x minus 10. And our g oops. Okay, so we have f and g in here. So when I scroll out, I'm actually going to change the x back to something better. Okay, so now when we're asked to find the area bounded by these two functions, we have this left side. There's an area bounded in here, but then there's also an area bounded over here on the right. So you have two different areas to deal with. But when it's asking for the area bounded by these curves, it's asking for the total. All of the area that gets fenced up between these two functions. So I'm just going to do a super rough sketch of what we're seeing. So G is this cubic with pretty big ups and downs. So let's start with that. Look at that one more time. Okay. So this is generally what we're seeing for G. F is doing something like this. And so we have two areas to focus on. We have an area in here, which I'm going to call A1. And we have an area over here, which I'm going to call A2. We actually can't calculate those areas at the same time. So this is another situation where we need to know from where to where we're integrating over. So we're going to look for the x values where each of these intersections happens. So going back to the graph, this bottom one is happening at -3. So that's our smallest x. And then this middle intersection happens at 1. And then this last one happens at 5. So we don't care about the y values at those points. We only care about the x's. So -3, 1, 5. -3, 1, and 5. So this first area, A1, is starting at -3, and it's going up to 1. So those are the limits of integration of just that first chunk of area. Which function do we put in first to calculate A1?
Gx.
Exactly, g of x. And that's that whole x cubed minus 3x squared minus 8x plus 5. And that's because g is the top function for that piece of area. G is on top. And then we would subtract the f. Then we can look at A2. Actually, I'm going to give some room here. So A2 is picking up where A1 left off. It's starting at 1 and now going up to 5.
And then switch them. 5x minus 10 minus
Exactly.
x cubed.
Exactly. So here, f is now our top function for that second area for A2. So that one has to go in first here. And then we'll subtract the whole cubic. So in this situation where our two curves bound more than one part, we have to look at each of those parts separately because they have different ways of calculating the height at any part of that area. So we do have to be super careful. G is on top for that A1 and F is on top for the A2. So our total area, which is what this question is really looking for, would just be each of those added together. So we can either calculate each of these separately, or you can put this all in one big line in the calculator, but in that case, we would still have two separate integrals. So I would rather do them separately.
I got the same answer for both.
And that is entirely possible. So let's check to make sure. So A1.
Yeah, I got negative 104 and 104.
Okay, let's see. So we have -3 up to 1 for A1. And that one has G. This is also a nice thing I like about Desmos is that you can copy and paste, which makes entering these things a lot easier. Minus F and we get.
That's what I got.
Okay. So that looks right. If we look at what's input here, we have -3 to 1. And we have our whole G minus our F, since G is on top. So that would be this first area. So then to find A2, I'm just gonna rearrange some things in here. So A2 started at 1 and went up to 5. And it's actually F minus, oops, G, and we did get 64 again. So that's not always going to be the case, but in this situation, the two sides of this curve and where the line is going through it are symmetrical. Just not always the case, so we can't count on that, but it is possible. So each of those is 64. So to get our total area,
128.
yes. So each of those ended up being 64. So in these kind of problems, the setup is what I am focused on when I'll be looking at your homework and test. So I want to see the setup of the integral, even if it's not simplified at all, that's fine. And then you can use technology to actually do those calculations. We have one application of this area at the end of section 6.1. Before we do that application, are there any questions about what we've done so far today? Okay. So we're going to see this area representations in section 6.2, where the area is not really representing real area. But in this section 6.1, we have a specific economics concept that uses area to represent income inequality or income distribution. So, starting with two axes. And these two axes are just going to go up to 1 on each, in each direction, +1 in both directions. So this bottom axis represents the percent of families in a country and that could be percent of households. It doesn't really matter what the definition of family is. This is just the percent of people in some way. And the y-axis is the percent of wealth. Let's say percent of income. So each of these is in a specific country. Doesn't matter what country. So what we're going to be looking at on this graph that's coming up is how much of the income families have. So I am going to draw an exact diagonal line here that's supposed to be exactly diagonal. This is the curve of absolute equality. And the equation of that curve is y equals x. So that's just a line with a slope of 1, and it's going through the origin. So y equals x is our curve of absolute equality. So what that means for these families and income is that if we were to go like here, let's say at a 25%, and since this is 1 and 1, these will be as decimals, but 0.25, 25%. 25% of families have 25% of the income in the country. And if we looked at, I don't know, 90%, 90% of the families would have 90% of the income. So the curve y equals x always has the exact same values for y and x on any point. So this is absolute equality because every family has the same portion of the income. 10% of families have 10% of the total income of the country. 80% of families have 80% of the income. So the income is exactly evenly distributed among everyone. So that's our curve of absolute equality. There's also a curve of absolute inequality, which I'm going to draw and then probably erase just because I think it's going to make things a little messy. Absolute inequality would be that if everyone has no income, no income, no income, no income, no income, and then at the very end, there's just one family that has all of the income. So absolute inequality would mean no one has any income until that very last 1% or whoever who has all of the income. But we're going to be comparing with the curve of equality anyway, so I'm going to leave that inequality curve out. So we have one more curve that's going to go on here, and that is called a Lorenz curve. That's supposed to meet right there. Okay. So Lorenz curve is a curve that represents the actual distribution of wealth in a specific country. So curve of absolute inequality is there as a reference. This Lorenz curve shows the distribution of wealth for a particular country. I should say income. For a particular country. So most countries do not have, probably say all countries do not have an exact equal distribution of income. Everyone is not getting the exact same amount of income. So a country is going to have a curve that looks more like this, where the maybe lower percent of families probably have less income, and then the super wealthier people are going to have more of the income. And so the way that the Lorenz curve compares with the curve of absolute equality can tell us how evenly income is distributed in a country. So that means that if the Lorenz curve is closer to the curve of absolute equality, then it has a more even distribution. If the Lorenz curve is farther from the curve of absolute equality, it's going to have a less even distribution of income. And the way we can measure that, so there's a thing called the Gini index, which maybe you have heard of if you've studied these things before. The Gini index is a calculation using the area between the curve of absolute equality and the Lorenz curve. So I'm going to bring up the definition of Gini index now. And this is also on page 387 as well. And I should have written one more thing here. Oops. Okay. Now we have some context here. So Gini index is this integral. So it's 2 times the integral from 0 to 1 of x minus f of x dx, where f of x is the Lorenz curve. So the Lorenz curve is this bottom curve that's coming down and showing how income is actually distributed. The x in front is our curve of absolute equality. So if we ignore that 2 for just a second, just this integral, that's exactly what we have been doing in our previous examples today. That is the area between the curve of absolute equality and the Lorentz curve. The 2 is just there to make the index a nicer range of numbers. So if we look at the area, just the area between those two curves, the biggest possible area is if we have that curve of absolute inequality where we basically have a triangle here. Oops. So that would be the very biggest area, but that would be an area of 1/2. So the Gini index, all it's doing by taking that 2 is making it so that our range for the Gini index is 0 to 1. So that's just there to make a nicer scale. Rather than being 0 to 1/2, it's 0 to 1. So there are a couple of things about the Gini index I want to say before we do an example here. Oops. Come on. So a couple of points. Gini index is always between 0 and 1. So 0 would be the case where the Lorentz curve is actually the curve of absolute equality, so there's no area between them. The 1 would be the biggest area where we have absolute inequality, where literally only one person has all of the income. So of course, 0 and 1 are not really achieved. It'll always be between those. The other thing to keep in mind with the Gini index is that smaller, I'm just going to abbreviate with GI. Smaller Gini index means a more even distribution. So the closer the Lorentz curve is to that equality curve, the more evenly distributed the income is. So if they're closer together, then there's going to be less area in there. So this is what the Gini index tells us. So as long as we know the Gini index of countries, we can sort of compare the distribution of income.
Do we need to memorize the Gini index?
No, that will be provided on the test.
Okay.
So here is our Gini index problem, which I will leave up there for a minute. So this is a lot of words for what we're looking for. But so we have this certain country, the Lorenz curve in 2013 is f of x equals x to the 2.6. So our Lorenz curves will generally be something a little bit weird looking like this, where we have x with like a decimal exponent, which is just fine. So economists predict that the Lorenz curve for the country in the year 2025 will be x to the 1.8. So we want to find the Gini index for each curve and interpret the results. So starting with 2013, our Gini index is always 2 times the integral from 0 to 1 of x minus the Lorenz curve. So that Lorenz curve is just going in there after the little x, and we can calculate that on a calculator also. So on this, again, I want to see that you know how to set up the integral, but from there you can use technology to find it. So we have the integral, and I should put a 2 out there first. 0 to 1. Ah, dx. So our Gini index is 0.44. And these, just FYI on the test, I said to round to 3 decimal places. I'm pretty sure that's what the book says as well. So we'll round to 3 here. So 0.444. So this is good. If you get a result that's out of the 0 to 1 range, then that's a good indication that something went wrong. But this is between 0 and 1, so that's good.
Does it need to be brackets or parentheses, or does it matter?
Doesn't matter. It's the same.
Okay.
Yeah, a lot of times the books and like formal definitions will use brackets if there are already parentheses. I personally just prefer parentheses, so that's what I usually write, but it doesn't matter. And so then we also have this predicted curve for 2025, in which case we have g of x equals x to the 1.8. So same thing. And this is one of those times when I like Desmos because we already have a Gini index in there. So the only difference is this exponent. So instead of typing the whole thing back in, we can just change that one little thing. And we get 0.286. So the last question here is, and interpret the results. So really that's asking, what does this tell us about this country? In 2013, the Gini index is 0.444, and the prediction is that in 2025, it'll be 0.286. So what does that tell us?
That it decreased or increased over time?
What increased?
So it'd be 40, basically 44%. Is it considered a percent or no?
It's not a percent. Yeah, it's just sort of the scale.
So then it went down from 2013 to 2015
So I'm just going to type some.
by 24.24.
Income is more evenly distributed.
Yes, exactly. So the Gini index did decrease. And what that means in terms of what's going on in these countries is that the income is becoming more evenly distributed. Yeah. So if you're asked to interpret the results or maybe compare when it was this more evenly distributed, a smaller Gini index always means a more even distribution of income, because it has that smaller area when we're looking at between the curve of absolute equality and the Lorenz curve. So this is one way where we are actually using this specific application of the area in between the curves, but we're taking that area and interpreting it to mean or to tell us something different. So even though we are actually calculating an area, we're then using that to do something else that's not area. So any Gini index problems will always just use this little formula, and that's it.
Is it ever likely that there would be a Lorenz curve that's concave down?
No, because if we, that's a good question. Let me draw a little. So like if we imagine that same thing, and here is our equality. So a Lorenz curve will always have to start at 0, 0 and end at 1, 1 because it's representing the percent of families who have the percent of income that's on the y-axis at that point. So 0% of families should have 0% of the income, and 100% should have 100% of the income. So those are sort of given. We have to start and end at 0, 0 and 1, 1 respectively. So if we were to have a curve that's concave up, this is not possible because this would represent the more, what am I trying to say? If we were to put all of this together, there would be too much income at the bottom part, and we would end up with more than 100%. I'm not explaining that very well. Let's see. Now I'm actually second guessing what I just said. That might actually be possible. Okay, the answer is still no, but it might not be because of what I was about to say. So basically, no, because we need to have the Lorenz curve below the income distribution for the purpose of calculating that Gini index, or else we would get a negative Gini index because the curve would have to go above it. I'm going to have to think about whether it would actually be possible to still show income distribution with a concave down curve. But no, sort of the general format of this is that the Lorenz curve will always be underneath. It always has to start at 0, 0 and 1, 1. And so it'll always be concave up to represent that. I'm going to think about this more and share my conclusions on Thursday. But the like sort of practical answer is that you will not see a concave down Lorenz curve. Okay, so section 6.2, which is what we're doing next, is all applications of definite integrals. So here we've seen one application of this area calculation. There are so many applications of integration, and so we're only going to get to a handful in this class. So I want us to just sort of mention a few, or mention one, and then we will start talking about a couple more. So section 6.2 is about applications in business and economics. The one that we're not actually going to cover in this class is probability distributions, but I want to mention it because I am not 100% positive on this, but I'm pretty sure that if you're taking business calculus, you probably have to take stats also. So maybe you have taken it or have not taken it yet. Yeah, I thought so. Unless you're just taking this for fun, but if this is required for you, then stats is probably required as well. So one of our most common distributions in stats is the normal curve. So for example, so I'm not going to get deep into this, but if you were calculating, for example, we want to know what percent of data falls between this X value and this X value. There are all sorts of technology tools that will do this for you. But underneath, what is actually happening is an integral. The normal curve is a function. It's kind of a nasty looking function. But if we want to know the percent of information that's between 2 points, 2 values, that is actually an integral from between those 2 values of that distribution. So when you look at z-tables in a stats class, or when you're using R or whatever to calculate these things, that's actually integration that someone else has already done that you don't have to use anymore. But there are different probability distributions also. So that's the normal curve. A common one is like the length of a phone call. It's supposed to say phone. So this curve would say that most phone calls are pretty short, a few minutes long. Some phone calls are much longer. But we can look at probability distributions that are different shapes, which I'm leaving to your stats class, but this would be the same kind of thing. If we want to know the percent of phone calls that are between 5 minutes and 30 minutes, we would just integrate that distribution to find the area under there. So probability distributions, a lot of what you see in a statistics class for like the normal curve actually has calculus in there. We just don't have to do it because it's already done for us. So that's one application that we're not actually going to do in this class, but it's just something to keep in mind. What we are going to look at are continuous income stream, which will be our first application, and consumer surplus and producer surplus. So neither of those things probably mean too much, but basically we will cover this in detail next class. But imagine you have a function that tells you that you're making some sort of income. If I can spell correctly. And the x-axis is time. We can figure out the total income at a certain time based on that area under the curve. So anytime we're looking, we are using this idea of integration. The area doesn't necessarily represent area. So here we're looking at income, maybe income per unit of time over so many, income per hour, for example, over so many hours. But it's not when we have a consistent income that we would use this, it's when our income might fluctuate a little bit. So we don't have time to really start to get into this, but this is what you can look forward to for Thursday, is we'll be talking about continuous income stream and these two things, consumer surplus and producer surplus. So that will be where we start off on Thursday. Have a good day. I'll see you then.
Bye. Thank you, Madeline. Have a good day.
You too. Thank you.
Thanks.
Thank you.
You're welcome.